Hi everyone, and welcome to day 3 of our webinar. Today is the third in a series that we've been doing on how to model raised floor data centers. And the outline for today is to review how to set up the model, how to run the model, how to analyze results, how to use crack parameter analysis, and then taking a look at reports, using reports and presentations and troubleshooting field simulations. That's quite a bit of material to get through. I'm going to try to do it in an hour. Little housekeeping once again. If you want to ask questions throughout the session, I encourage you to do that. The questions should be submitted. I think the best way to do it is to type them into the question section. That's worked pretty well in the past couple of days. And just type in your question and submit it. I will see it because I have the questions coming in on a different monitor. I can see them and I will try to respond in real time to any questions you might have. I can also open up microphones. We haven't done that yet. That doesn't work as well because of feedback and so forth, but type them in. I'll try to get to them, and feel free to reach out to me after the session if you want, and we can talk in more detail. So let's get right into it. First of all, let's talk about setting up a model for simulation. And the first thing you'll want to do, and I've got a few PowerPoints here. I'll go through the PowerPoints and then I will set the PowerPoint aside and open up the interface again and go ahead and show you the interface and how it would work inside of CoolSim. But let me just go through what you should do before you submit a model. First of all is the model description I tend to use. This is just a place in the interface that I'll show you where you can put in comments, put in what I use it for is boundary conditions or assumptions. I list my assumptions in the model description. And the reason I do this is because it comes out in the summary report. And I often export my summary reports from CoolSim and just leave them so I can look at them later. But I often forget what assumptions I made in the model if I don't make some notes. And oftentimes we use file names to try to remember what we did, what assumptions we made, and I find that actually using model description is better than trying to use the file name to annotate what it is you've done to the model. So model description is something I will show you. Presimulation report is important. This is a CoolSim feature, but in any kind of case, you'd want to always review your input parameters and make sure they're set up correctly. So I encourage people to do that. It saves time because oftentimes you'll make a mistake on keystroke entry or things are out of whack. Presimulation report shows you that and kind of gives you a feel for what is being fed to the cluster. Post-processing parameters, if you want to use the standard report, you don't have to do anything in this section. But you may want to set them up differently. We do allow you to set up post. Post is a script in CoolSim. It runs automatically, but you can set the parameters differently than the ones that are defaulted in case you want to do something different. Crack parameter analysis we'll go over. That's the opportunity to run multiple simulations from one input file up to 4 right now. Density, mesh density, we'll talk about a bit. We really only have 3 levels. Coarse, medium, and fine. I'll talk about when to do which one. Submitting the model and then polling the progress if you're interested to see how the model is doing. So let's begin to walk through this list. Here is what again, this is PowerPoint. I'll show you the interface in a moment, but here's what model description looks like. It sits under the edit key or edit menu item, and it's just a tabular entry. And here you see I've made some assumptions about this model. This one is, a certain load and has a certain number of racks. And most of this will be reported in the summary report as well under model description. But it's nice to have this because you can just put in what you want to put in. Here, for example, I had slight resistance I added on each rack. Just notes to yourself about what you've done, so that when you go back to look at some results that were there from an earlier model, you can remember what assumptions you had. That's really all it is. The only trick here is it doesn't refresh itself when you do a new submission, so you have to remember to update it before you submit. Sometimes these get stale and they have notes on them that don't reflect the current model because I forgot to update it. So it's a thing to remember to do. Just remember to update the model description before you submit. Presimulation report sits right here. There's a little icon in the upper right-hand corner that is on the simulation side. By the way, there's a line here, a slight line in gray that shows the items to the right. These are the items necessary to run your simulation. So the user interface is kind of broken into three sections. On the left are the objects, in the middle are tools that you might use, and then over on the right are simulation submission actions. Presimulation report is here. You see it comes up and it shows you a couple of things. The one that I always look at right away is the ratio of airflow coming from the cooling unit to airflow demanded by the racks. This is sometimes referred to, if any of you have been to DCEP training, this is the RTI ratio. And you want it to be fairly close to 1, but you don't want it to be way off. If you notice, I pulled this one on purpose because you can see here there's quite a difference. The cooling units are supplying 245,000 CFM in this case, and the racks only need 84,000. Now remember, the rack's flow rate is proportionate to its load at a ratio of about 156 CFM per kW at sea level on a 20-degree delta T across the rack. So what's going on, I suspect, in this case, I do know this case because I worked on it, the room is not yet fully loaded. 245 is the full capacity of the cooling units, and the racks only need 84. So normally that would run and just loop back. In other words, the air coming out of the cooling units would just cycle back to itself. But in this particular model, they used containment. And this is often a case that I see where people have used containment, particularly cold aisle containment, which blocks the cold air from entering anywhere other than through the racks. And the racks are limiting the flow rate to 84,000 because that's a boundary condition. Those are both boundary conditions, and they'll compete against each other and cause the model to fail. So it's important to take a look at these ratios and make sure they're fairly close. This is an example of one that's way off by a factor of 3. And if the customer in this case has used containment where they're not allowing recirculation to occur or bypass airflow to occur from the crack to itself, then the model will fail because of pressure. You see these delivering 3 times more than they can accept, and therefore the pressure would build to infinity, and yeah, the room would blow up. So the racks are not made to leak extra fluid through them or air through them. They're going to run at just exactly what you set them, and this is kind of an issue with CFD. It does what you tell it to do and no more. It can't make assumptions on your behalf. So it's important to review this. The other thing down here is the crack details and rack details and PDUs. Those are hyperlinks, and it's a fast way. By hitting those, you can edit directly from this report. So if you wanted to make changes to the system, and instead of going into the user interface and touching each of the pieces of geometry and opening the editor, you can get at the data right from here by using these hyperlinks, which is just handy. So setting up a post, as I mentioned, the way this system works is you run a post-processing script on the cluster. That's part of the sequence for CoolSim, and we do that intentionally so that A, there's consistency about what's being run, and B, you don't have to spend a lot of time doing it manually. Most analysis systems, CFD analysis systems, require you to post manually, where you're creating each image manually and setting it up and redoing it. And when you're driving to optimize a particular design, that's tedious. It takes a lot of time. So we automate that for you through an automatic report generation system. That's the good news. The bad news is it has historically been fixed. It was set up to do certain things, and people would often want to change the position of the cut planes or change the position or the ranges of temperature or color. So we've allowed you now to modify it, and you do it through this little button up here, and allows you to flip these switches. We do offer temperature clouds. These are ISO surfaces, not used a lot. Animations are normally off only because these take quite a bit of time to produce. So this is a time issue and also a size issue. The download gets bigger when you use animations. and so the download time for results takes longer. Velocity contours, not a big deal in data centers because they tend to be relatively low velocity kinds of environments. However, the tool is actually being used to do more than data centers these days, UPS rooms and other things. So velocity contours have become of interest. The rest of these are all related to temperature contour, setting the contours correctly. How many do you want? Where do you want them? So you can have up to 10 additional cut planes anywhere you want for temperature, pressure, velocity. Over here is just ranges. You can set the range the way you want. You can set the number of path lines the way you want. So it's important to just touch that before you run to make sure it's set the way you want it. And then if you're interested in doing parameter analysis, right now our parameter analysis is for cooling units only. Someday it will expand and offer you other parameters. I have been asked for other parameters. But right now we have cooling units, and you can run up to 4 variations at a time. So you would turn this switch on. It's under the simulation menu item. And you're able to set the on-off state with a set of switches like this. So you can see in this example, we have 7 cooling units. This particular one, I called them fan assemblies because we're modeling a free air system or a air side economizer system. But you see here in run 1, so run 0, they're all on, and run 1, I've got one shut off and so forth. So I'm beginning to study the effect of maintenance modes or down modes on the various fan assemblies. And you can't see it, but under airflow and temp, I would set those parameters accordingly as well. So in this run, we're assuming that VFDs are in effect, and what would happen is in run 0, they'd all be running fairly slow. In a run 1, you'd have to ramp these others up to compensate for this guy being down, etc. So you can run multiple simulations off of one input file. The download is bigger, and the output report is more complicated. It's just times n, so there's really going to be 4 reports. There's a summary page first. I'll show you that when we get to the interface. Mesh density. Mesh density is set up as a coarse, medium, and fine, is how we did it in CoolSim. Now, meshing can be a whole subject in and of itself. We're using automated meshing here. This is hex-dominant, body-fitted, non-uniform hybrid meshing that we're using. It's an Ansys technology. And it comes up when you hit the Solve button. When you click Run over here, run means run the simulation, of course, and you'll get an interface that looks like this one. And the number of jobs you can run and the number of processors you can access is a function of your subscription. For many of you, it's just one job with one core. But if you have a subscription that offers more, we can run each job in parallel if in fact they're big. And Fluent is fairly linear in its performance, so as the number of processors grows, the time to solve it declines as a ratio of the number of processors, inversely proportionate, as long as your mesh is big enough, I should say. So if you've got a model that's fairly complex, putting it on 4 cores will reduce the time to run it by a factor of roughly 4, and so forth. And then the other is number of jobs. How many of these can you submit concurrently? That's another option in our price list where you can submit multiple jobs concurrently, and each of those jobs can run multi-core. So that's a kind of a nice system that is a result of, again, I'm leveraging Fluent technology or Ansys technology, so that is coming from them, but it's going to allow us to have tremendous upside in terms of complexity. So we will, as computer costs continue to decline, offer you more and more capacity at the same price. Down here below, we have entire solution or post. Now, in the recent edition of CoolSim, you can run post only after you've already made a run. Now, let me point out here that, so you run a simulation and you get results back, and say, for example, you want to change the position of a cut plane, or you want to change the range of color, tighten up the color, so you're looking at a tighter range of pressure or temperature. You can do that as a subsequent submission and run post only. To do it, however, you do need to have this switch flipped right here called Store Simulation Files. These are the what we call case and data files. These are the mesh, well, actually solver output files that have to be stored, which are usually fairly large, and we tend to delete things off the cluster for security purposes. So unless you flip that switch, those files will be gone once you download the results. So if you flip the switch, they'll stay there at least for a while. We don't leave them there forever. I think we've got 3 or 4 days set. I think it's 3 days set right now that they'll stay there for. But what it will do is allow you to rerun post if you want to rerun post. And the way you do it is to just go back and set up your post again with your new cut planes, whatever you want, and then flip this switch, hit the run button of course, and flip this switch that says post only. Mesh density doesn't matter because you've already meshed it, and you just submit it, and it will rerun post. Post is quick, generally takes 10 minutes at the most to run the post script, maybe a little more depending on what you've done, but it's fairly fast as compared to other methods. I did just get a question about what is the mesh method that we use in CoolSim. CoolSim is a hex dominant, body-fitted hybrid non-uniform mesh. So it is hex core. It uses hexes wherever it can, but as it gets close to angled surfaces or round surfaces, it will switch to tetrahedras and or prisms, mostly tetrahedras, on the surface, so that you get a nice close body fit on anything that's got a non-irregular, non sort of hex shape, such as an angled wall or a round object or whatever. The technology is quite good. It's the same technology as used in IcePack because electronics packaging and data centers tend to share similar characteristics. So yeah, hex dominant, hybrid, so it's mixed cell, non-uniform based on geometry. So the density of the mesh changes as the geometry gets tighter. That's, of course, a problem for small gaps and things like that. You have to be careful because the mesher will generate a tremendous amount of cells in areas that are small. And it is a non-uniform. Yeah, I guess that's what I meant. All right, so then you submit the job, and this is a point in time where it hits the internet. Otherwise, you're running local. It hits the internet and submits a job and passes it off to the cluster. Now, I'm old enough to remember this was done back in the 1980s. Same idea. This is not a new idea, the idea of handing your job off to a cluster. We used to do it in supercomputing, where the local machine would be a Unix workstation and the remote machine would be a Cray or whatever, and you would set up your models locally and then pass them to a cluster. Same idea here. It works very well because it makes the desktop unit primarily an engine for creation of the model and viewing of results, which it's quite good at. But CFD can be heavy. It's memory intensive. It wants lots of disk and computationally intensive, and it turns your computer, your local computer, into a bit of a slug if you run a big job. So this just offloads your desktop and allows it to run. We've automated it so it's nice and easy. You just push a button, it touches the internet, it uses secure interface protocols, goes to a cluster that we have put in place specifically for this. It is a private cluster, and it runs there, and then everything is deleted on the back side. We do allow you to poll. This is kind of a tail idea. If you're a Unix user, you know about tailing files. This is a tail idea where you can click on this little status button in the upper right-hand corner, and it will tell you where you are in the sequence of solution. We've broken this sequence down into 7 steps. The job upload is the first one. That means it got there. Sometimes this doesn't happen. You do run into cases occasionally where you've got an internet issue and for some reason it doesn't make it. So once you've submitted a job, it's important to usually hit this little button and see if you've at least made it into Mesh. The sequence of upload input file generation to Mesh, this sequence right here only takes a few seconds generally, or maybe less than a minute. So generally what I do is submit and then hit this status button to make sure that it's gotten to Mesh. The Mesh sequence can be long, long being, minutes, 20 minutes is long, 30 minutes is very long for a Mesh. Generally Mesh generation happens pretty quickly. In a few minutes it happens. Equation solution is the long one. That's where we're running the Fluent solver, and we're doing, of course, the calculations on each one of the surfaces of the cells, and that can be long. It's proportionate to mesh size, so long is a relative thing, of course, but it's not unusual for a model to take, simple ones will take 10 or 15 minutes. A more complicated one will take 20 to 30. A fairly complicated one will take an hour. A very complicated one will take, a few hours. I've seen them take 4 or 5 hours on multiple cores. So it depends on your complexity of your design. The more detail you put in it, the longer it will take. That's why I encourage you to only put in the detail that is necessary and no more. Don't add geometry detail to your model unless you know it's needed. Keep it simple. That way it runs faster. You can view the results more cleanly. Remember that as you increase the mesh or the complexity, which they're correlated, that means you're going to get more output. And as you get more output, it's harder to see what's going on. It gets cluttered. Graphics generation's quick, usually a few minutes. Report generation's a few minutes. Download can take some time, depending upon your internet connection. Downloads are getting bigger, particularly if you run crack parameter variation. Downloads can be, several hundred megabytes of size, so you're pulling that down over the network. There's been a lot of discussion about should we be pulling them or should we view them remotely and just leave them there and only pull them when you need them. But at the moment, we're pulling it all down because most customers want the results on their local machine when they're done, for a variety of reasons, which include security for one, and number two, storage and access, and you can take it with you, etc. So that's where we are right now. We're still downloading results. This may change over time. We may give you the option to leave it up there, but right now it's all downloaded. And by the way, it's all deleted. After a couple of days, it disappears, all the stuff that you had there. So after you launch the job, notifications are sent to you. There's a start email, a job complete email, and then if you succeed, you'll get a summary report attached to an email that says it's successful. If not, you'll get an error log. So what I'd like to do now is just jump out of here and start to take a look at some of these error logs, because I want to review a few of them, and I also want to review some models. So I'm going to pop out of this interface here, and I'm going to go over and use CoolSim, and we're going to take a look at some models. I think this works pretty well. First of all, I want to take a look at some failed model examples and show you why certain models fail and so forth. So let's first take a look at this one I put together for the class. This is Demo Data Center Mesh issue number 1. And this one failed. I failed these kind of on purpose. And what I'm doing here is showing you why something failed and how to get it. So let's just kind of review here a little bit what we're doing. Let's take a look at my few things about this model. This one does not have any results, so the results live in this report tab down in the lower left-hand corner is where I'm pointing, and I'm toggling between the report, which doesn't exist, and the design. If I hit the status report here, it'll come up. It comes up, by the way, on my other machine, on my other display, I mean. And it says that it's failed. So I connect here and it says the job has failed. It failed in mesh. So a failure will occur in a few areas. Mesh, solve would be the two areas. It's very unusual for it to fail in graphics or report generation occasionally, but it's rare. Upload is pretty obvious. You're just not making the connection to the cluster, so you've got to try it again. So mesh generation is one of the places that it'll hiccup, and it's fairly easy to fix. And I'm going to show you how to do that. So here it says the simulation has failed because either the mesh was not generated or it was of bad quality. Check to see what that status looks like. So I'm going to open up the failed model example here. Let me just, failed model examples, and I'm going to open the file that comes back with it. Now these are just text files. They're log files. They come back with the email that comes back to you. So the email comes back and you get this log file, and I'm just going to open this up and show you what it looks like. It can be a little cryptic because it's coming from the server, it's coming from the modeler itself, the Fluent modeler. In this case, it's coming from the mesher. So you can see that we try to feed back to you. We parse the log file and we send it back to you. And, you know, we go through this sequence where we say, well, we're checking this and that, you know, heat load pass. This is if you made a mistake in heat load, by the way. Never put a 0 heat load in, right? So you have to be careful of a few things. Heat loads need to have a number. They can't be 0. So we pass that. Flow rate of cracks. Cracks can't be set at 0. I mean, CFD in general doesn't like you to put things in it and then set the parameters to 0. Either put them in as blocks or don't put them in, or give it 1. Give it a value of 0.01. Give it a value, but don't put it in as 0. Cooling parameters passed. Everything looked pretty good, and then it started to try to generate a mesh, and it went, uh-oh, I got a problem here. There's a problem with something called baffle 1 and baffle 0. Everything has a name. Every object has a name, and it's complaining here that it had a baffle problem. Now, so what you have to do is go back to the modeler and find that thing. Now, these objects all have names, but they're a little hard to see. And we have fought with this on and off in my life, trying to label things correctly. You know, and if the label is too big, then the model gets very busy with these big labels in this scene. So the way that we do it, and right now it's kind of where we are with CoolSim. It could be a little better, but you can, with a rubber band, which is a control key left mouse key, draw a rubber band around a set of objects, and it will generate for you a tree. This is a dynamic object tree. We don't do a static one in CoolSim. We make it dynamic based on user need. Otherwise, usually in modelers, many of them sit over here and sort of take up screen space, and they're static. We do ours dynamically, and you can just look through here. First, turn them all off, turn everything off, and then look for your object name, and then just click it. So baffle 1 is right there. Oh, there's baffle 1. Now you have to say, well, what's baffle 1 doing there? So you go down and take a look, and you see baffle 1 was a mistake. Baffle 1 got stuck inside this rack by accident. So you can remove the rack out of the way and delete baffle 1. This is something that happens. The other thing, and I did this intentionally because I've seen it before, you can do this for the whole room, by the way. You can highlight the whole room. It makes the list longer. But you can highlight the whole room. Again, control left mouse key, highlight the whole room. Click off the selection of everything and only select what you want. There was also a baffle, another baffle that was causing trouble in here as well. So, but I guess I already deleted it. I guess it was that one. So I thought there was one under here as well. Nope. The other thing, remember to drag your stuff out of the room, let it snap back. All the things on the corners, let them snap back because you don't want a gap behind those things. You want them to sit nice and tight against the wall. Just let them snap. So that was that model. Let me bring in another one here and take a look at it. Mesh issue number 2. And I'm just showing you different things that happen so that you can avoid these kinds of mistakes and avoid any issues you have. We'll start to get into results in a moment. This model as well, same model, but when I submitted this one, it also had a mesh issue, I believe. So here, let's hit status report and see what it says. And my job status says, yep, got a mesh issue. So let's go take a look at that mesh issue. This was, I think, number 2. Mesh issue number 2 right here. Yep, but I don't see the log report. Tile issue could be this one. Open Notepad. This one says that, this is a very common one I see as well. Tile rows, you know, again, it passed everything up here. Our heat loads are fine. Everything looked okay on the input, but we've got a mesh issue with tile row 512 and really tile row 5. Tile row 5 is problematic. You will see that we try to mesh it a few different times. First mesh was created, it failed. We went for second mesh. It failed. We went for third mesh. It failed, running third attempt. So we go after the model 4 times actually, to try to get a mesh, to try to get a good mesh. And each time we do that, we're running a script that we've developed over the years that resets certain parameters. In a meshing, what you try to do is you try to close gaps yourself in the mesher. They try to clean up the geometry in mesh, and we're relaxing those cleanup things. You see the fourth attempt was not generated, so we stopped. So let's go see if we can find this guy. This is tile row 5. So let's go again, take a look, and I'm just going to flip it into top view here. And I'm going to just I usually grab a section at a time and highlight it. And let's just go down here, rack row, baffle. There's baffle 1. There's tile row 5 right there. All right, tile row 5 is having some trouble. Now, the most common thing that happens is that people double paste things by accident. These are often accidents. So let's see what we've got here. Now, the way to tell if something's on top of another, you can't have one object on top of another object because the inlets and outlets will get blocked, and it will fail and solve, or fail and mesh as well. It can't get a mesh on it. What I always do is just pull it, see if there's anything behind it. And generally what you'll find in, it looks like I'm looking at the old model. Generally what I'll find is that, mesh issue 1, don't save. Generally what I'll find is there's a mesh on top of a mesh, and that's what I had done, or a tile on top of a tile. That's what I had done in this model just to illustrate the point. So let's go to top view again. There it is right there. You can see it now. So I just highlight this section, deselect. Let's take a look at tile row 5, and you can see right there, now there's something going on. So let's go take a look at tile row 5, and if we pull it, you'll see there's one underneath it. So this is a case of just a simple paste on top of one another, and all you have to do is delete it. So meshing is fairly straightforward. We do support Control-C, Control-V, and sometimes it's easy to hit the Control-C twice. Sometimes it's required. By the way, look at that gap right there. That's not a good sign. We do have tools to close gaps, like select, and by the way, this is all available. Any of the things I show you are available on our training and support site and through video up here under Help. This will take you to our site where we show you how to do these things. But I have a close gaps feature that we've added. I can highlight that block. I can highlight this block. And then I put my cursor over the one I want to hold constant. And then I can close gaps in, remember my X direction is horizontal origin towards the upper left-hand corner. And I can close gaps. So that's important to do on anytime you're in a model and you see a gap. So that was the one here. I think in this one I actually buried a baffle in here. Nope, guess not. I thought I did. So mesh issues, pretty easy to resolve. Now you'll also run into some solve issues as well. Those become a little tougher to solve. And let's see if I've got one here. Ducting with baffles. This one may have failed. When you've got a solve issue, it's usually pressure, and it's because the pressures weren't balanced correctly. In other words, your crack units are supplying way too much air for the ability to consume it, or there's an isolated area, an isolated volume. So here's an example here, and it's important to understand these things. It gets a little tricky when you're doing containment. Now this is a contained environment. What the user has done here is to create a model. They have their racks are detailed here. By the way, I can right mouse click and nearly hide or hide. So I'm going to nearly hide so we can see what's going on inside of these baffles. So what the customer has done here is made passive chimneys for each one of these things, and they've put servers in there. And you can see the servers sitting right there. They're blowing front to back. The user has put a rack rail in, so there's some leakage there, and a front face on it. So that all looks pretty good. I mean, it would normally be fine. Now what the users remembered to do is to punch a hole in the ceiling so that the air can get out of that chimney. It's very easy to forget that little guy because, you know, that looks like it's got a hole in it, but it doesn't because the ceiling is transparent. So this looks pretty good. They've used extensions on their cooling units. They did build, it appears, these structures underneath, which are not really necessary because you can use the turning vane, which is just a function in the editor. So you can turn a turning vane on under geometry, and you don't need to build those uniquely. So turning vane is right here. So they could have put a turning vane on, and there it is. It needs to point the right way, by the way. I see this a lot, where the turning vane, the output is pointing out of the room, so that outlet's blocked, and that model will fail because the outlet's blocked. It's up against the wall. So pay attention to your arrows and direction of flow. So in this case, we'd have to rotate this guy around 180 degrees using the rotate command to get it pointed correctly. We'd have to delete those baffles here because we don't need them anymore. So that's just a click and a delete. And then you'd flip it into, you want it up against the wall, right where it was, so you'd snap it out and let it drop in. So that's fine, but this model did fail, but the reason it failed is not immediately obvious. You look at it and you say, well, it looks pretty good. Well, why would it fail? Well, let's take a look at the pre-simulation report and see if we see any unusual things going on here. And there you have it right there. You see the racks only need 20,000 CFM, and the cracks are delivering 42. Now in this case that may cause a problem, but may not, because it allows leakage to go through here and up into the ceiling. So that may not be exactly why that one failed. I'll have to take a look at the log report. And again, this is what you do. The log reports come back. Demo data center, ceiling plenum, duct through ceiling plenum, ducted with baffles. Let's take a look at this. You can open these with any kind of editor. So rack row 247, 240, oh, I see. So it's got a problem with the racks itself. So you say, okay, well, something's going on with those racks. Where is rack 284? And again, the way you find it is to use that same method I used before. So let me flip it into top view here, and let's take a look at rack 284. I'm going to select just a few of them. The individual servers show up as racks in the listing because it uses a rack row concept. So let's take a look at rack 284. We just go down the list until we find it, and then we just click on it. So we scroll down until we find 284. I didn't highlight them all. There's 289. 284 right there. So 284 is sitting in this group. All right, second one in. So then let's just flip the 3D view and go take a closer look at that 284. So it's sitting right in here. So and let's you can also hide. Let's hide the baffles so that we can take a good look at what's going on inside. So I just did a hide. And by the way, if you hide something, it doesn't include it in the simulation. So be sure to show all before you're done. There's 4. Now chances are that there's something going on here. I'm clicking on these and I'm getting the 4s and not the 2s. Chances are, and so what I tend to do is to move them, and you can drag them if you want, but sometimes I don't drag them because they'll move in both planes. So what I do is I just go in and move them in one direction. So let's say start Z, and I move them by a bunch so that it gets them right out of the way, and then you can just put them back there when you're done. There's nothing wrong with that one. And what I'm looking for here is something pasted on top of one another is not unusual, for example, to see something pasted. So all I'm doing here is moving it by a big distance to see if there's anything. Oh, you see I moved that one, and yet the server's still there. So let's see what this one is. There it is, 284. So we had when the customer was doing probably a clone, they were cloning these, they just simply cloned twice and got that one on top of itself. So I just removed that one. That one's gone, and then I put this one back by putting the 5 back in front of the 3, and I'm back in shape. So fairly easy to find meshing problems. Meshing problems are not too hard to resolve. and then you can go ahead and solve. The only other issue that will show up beyond meshing is usually pressure, and that can be a function of imbalance between supply and return, or sometimes situations like this. This is a tough one for a mesh to generate right there. It's actually a little better if there's a gap. If I had this tight against that angled wall, that's even harder for the mesh to generate a good mesh in that. And mesh quality does make a difference and will cause some issues to occur sometimes in solve. That is when you may want to use a fine or a medium mesh. If it fails in solve and your pressures you believe are okay, and again in this case I think they are because there's leakage that occurs, and let me show all again so we can see this model. But leakage is going to occur through that rack. In other words, pressure is going to be able to get up into that ceiling because it's not a sealed rack in the sense of airflow. So this one, if it fails, will probably fail because of a poor mesh quality. Quality means that the angle is incorrect, the skew is incorrect, or the aspect ratio, the shape of the cell is not correct. So sometimes that'll occur. And I just turned everything back on there. So let's take a look at what else we have here. Here's one that I, interestingly enough, ducked through ceiling plenum. Let's take a look at this one. These are just, again, examples of rooms that I put together for purposes of discussion, and I want to get into the output reports here and show some of the output report and how to take advantage of those and how to view those and how to understand those. Now this one is run, and you can tell it's run because when it comes up with the output report. So this is a good one to start to look at the output report on. And I was trying to illustrate this to you when I was preparing for the class. I was trying to illustrate to you a failed situation based on a dead zone. So a dead zone is an isolated volume in the model where no air can get there. The CFD requires a continuous volume of fluid in order to do its job because it's actually interpolating values across the mesh. So here what I have is an isolated volume in the ceiling. You see the ceiling is sitting there, and outside of this duct work, which is sealed, there is no way for the air to get from the room into the ceiling. The volume of that ceiling is isolated. And so this had failed at 4.4, and it was a test case, so I kept it for 4.5 and thought, well, this would be a great example for you all to see because it's going to fail in solve. Unfortunately, it didn't fail, it passed. Now, we did upgrade recently to the new Fluent solver, Fluent 16, and that is pretty robust. Robust enough to be able to handle this case. And this case should not have passed. I mean, according to the rules of isolated volumes, this shouldn't have passed, but it did. So, but it is a good example of the ability to put ductwork in a ceiling. Now, best practices for this is that I would have put a grill right here. I would have dragged a grill in there, and this is a ceiling grill. I would have put it over here in the corner. I may have made it small, so you know I could make it as small as you want. There's not going to be any pressure there, so I could have made it you know, a very small little space, 0.5, 0.5, something like that, and that would have gotten rid of my issue associated with an isolated volume because this ceiling is sealed. There's no leakage in it, but it did run. So let's take a look at our output. And the output in the new version of CoolSim comes like this. And I'm going to spend a little time just showing you around here because there's a lot of data here and it's good stuff. First of all, these carets open the reports. This is pretty standard practice for output reports or HTML reports. This is all HTML. And you see here if I hit that caret, then this goes smaller and I get all of the various plots and graphs. Again, the position of these and the range of these are all 3D slices. So the position of these and range is a function of what you've got set in your post-processor parameters. And we now pop a separate window, and by the way, you have to use IE. This is an ActiveX window. So you can see here that I can pop a very separate window and I can zoom right in and get very large and view this any way I want. This is the little 3D viewer that comes with CoolSim. This is coming from Ansys, and it's free. So you can use this anytime you want on any machine you want, including take it with you and use it in PowerPoint presentations or what have you. It also comes with its own little interface, which is available through a question mark key. So I hit the question mark key, I get the option in this little viewer to do many things, including edit, which edit allows you to clean the model up and to hide blocks and things like that. So if I hit the edit key, this little menu comes up. This is a new feature, and I'm able to clean up the model a little bit, and I can do things like turn off block surfaces or turn them on, or turn off inlets or on, and what have you, and get a better view. There's also shortcut keys, so you can X, Y, Z, the model. You can turn off perspective with N. These are just shortcuts, and this is all, again, detailed in the user reference guide under the help command. If you want these keystrokes, they're listed there. If you ever forget, you can simply hit the question mark button. But one of the things that you can do that's quite nice for generating reports is create a PNG of this image in any orientation you want, at any aspect ratio you want. So say, for example, I wanted, right now I'm using full screen, so my aspect ratio is looking like it's probably about 4:3. But if I was making a Word report, I may want it to be more like a 1:1 ratio, which is a little squarer, something more like that. When I hit the P key, P stands for print, it'll generate for me a PNG of that file. So you can see it's brought up a little interface here, and it will take this file, which is a CVF file. That's the extender at the end of it, and it'll turn it into a PNG file, and you can put it wherever you want. Navigate to wherever you want and just generate those. And so you can zoom in and show somebody something. Hey, you know, we've got asymmetry coming out of these outlets. They're not delivering the same amount. Let me show you that. You can also show it in another view here from ducts and diffusers. This is airflow coming out of the duct itself. So this is another shot of the same thing, only from the diffuser right there. There's another shot that shows you flow rate on ducts. So this is a flow rate plot. It's showing you the amount of air coming out of each one of them as a function of color. And you can see one of them is generating about 1800 CFM, and the other one is generating about 1370 roughly CFM. So these are different ways to view it. So we have all of these cut planes and so forth. I didn't have animations turned on, so you won't see those. Now over here, data center description, this is again important to take a look at. If I had annotated it with text, it would have shown up here. Model ID, it would have been there. I didn't make any notes on this one. We have to take a look at these ratios. Racks want 3200, cracks delivering 3200. That's a nice balance. That's what you want. You want them to be close to 1:1. So you can walk through this report and view it. You can view the racks themselves. We always highlight the hottest one and the coldest one, and always tell you whether they pass or fail the ASHRAE standard. We do min, max, average for each one. We also do cracks. This is an important one to look at. We're supplying at 60. We're returning on an average of 78. Flow rate is 3200. We're dumping 18 kilowatts from it. Even the duct. So every object in the room has its own little report. This one's pretty short. These are the two that I was showing you. So we have analytical results in addition to graphical results. It's all automatically generated for you, and you can export it. This is important. Export report. Now we do this intentionally. I always felt it was, when I was working for these companies like Ansys and Fluent, I felt it was not right that we didn't allow users to look at their results after the event was over or after the simulation was over, without opening the application itself. So we gave you a way here to export the entire output. And here I'm just going to, I'll put it on my desktop for now so you can see it. So where is my desktop? I'm just going to dump it onto my desktop so we can have a look at it. So there's my desktop, and I'm going to now just say, okay, export. It'll export the entire set of results and open it in an HTML browser. So now if you look at my address bar, I'm looking at desktop, duct through ceiling plenums, data center report. And that is something I can open anytime. So let me just go to my desktop here, my desktop, and take a look at that. The duct through ceiling plenum, there it is right there. It's a folder. If I open it, you'll see it's got the data in it. Now, this is the full assembled report. If I right mouse click this and open with IE, by the way, you need to open it with IE because we use ActiveX, and IE is the only thing that supports ActiveX for the 3D images. It'll fully assemble and look like what I just showed you. But in addition, you can go inside here and, for example, if you want to look at the PNGs by themselves, we give for you a whole list of PNGs here. These are made automatically for you, and they're just straight PNGs. And they do have a particular orientation to them. So, you know, and they're in a 1-to-1 aspect ratio with an isometric view. But these are very handy to put into reports very quickly to show customers without having to have you do it. So they're just convenient. There's rack temperature inlet, cut planes, etc. So those are very nice to have. In addition, we allow you to go right at the 3D files. These are CVF files, and here are all the 3D files. You can open these directly too with a double click. So you just open them up, and here's the cut plane coming. And you can view them and do the same thing here that I was showing you before. The reason I point this out is that this is fast. Once you dump, and you see me dumping quite a few of them out, I often dump my results out so that I don't have to open CoolSim and then load the input model. The input models can get kind of big. You can see the size of them, they can get kind of big. So dumping these out is just a faster way to get out the results without having to load the application each time. And the only thing required to do this is the little viewer has to be loaded, and that viewer is free, and that viewer is a simple install on any PC. So you can take this with you and give it to customers or present it. I'm working on a consulting case where I gave the customers the viewer, and then they're able to view all the output themselves without having to have me display it for them. So that's a very, very nice thing to have. So that's a quick overview of how to look at results. The ones that are most important are probably crack performance. Take a look at this one. This tells you a tremendous about what's going on in the room. Of course, data center description, I always go here first to make sure my input parameters are correct. So here, yes, I did want 18 kW of load, 20 kW of load. Heat removed by the cracks is 1853. So you say, well, where'd the other two go? It went through the walls. So we do allow leakage through the walls, and you can set that up with a constant leakage factor, heat transfer through the walls. So let's see what else we have for objects here. This first one was duct through ceiling, so let's do ducting with baffles, duct through ceiling. Okay. So I've covered most of that. Let me just check back on my PowerPoint here and see where we are. I have reviewed results a little bit with you, how to get at results, how to look at results. These 3D images are very, very handy and very easy to use. Let me go over some tips for success in terms of solution. Try to keep your models fairly simple, as simple as you can, as I mentioned. Watch out for gaps. You notice in this left-hand model there are gaps between racks. Now, in fact, there may be gaps between racks in real life. The question you have to ask yourself is, does that make a big difference on the output? Is that changing things a great deal? And you have to make a good judgment about that. Is it okay to eliminate those? Are they going to make a big effect on airflow? In this case, they are not. They're too small. So by tightening them up using a close gap feature, you can reduce the cell count. So here we went from 3.7 million cells over here on the left to 2.8. We saved about 1 million. Solution time dropped by almost an hour. Output stayed the same. So if you're interested in understanding whether or not the detail makes a difference, start with a simple model, look at the results, and then add the detail and see if it made a difference. And if it didn't, keep it out and show the customer that it doesn't work. Avoid gaps. I talked about this a bit. Gaps behind things against walls is always something that people do or have a tendency to do. Try to avoid it. Drag things out of the room and let them snap back. Even this gap in here, I would probably leave that at this point because the product's good enough so that it doesn't bother it too much. But here, if you tighten it up, it'll run faster for sure. Again, gaps, I mentioned one of this earlier. I saw one and tightened it up. Gaps behind cooling units is common to see. Tighten them up. Use the close gap tool to tighten things up. Simplify geometry. It's very easy to try to make it a CAD product. So here on the left, someone went through an awful lot of detail to show the output of these cooling units, or return. I don't know if it's an upflow or downflow. But really, this one over on the right is much simpler. It's all one flat surface on the front. The mesher is going to have a much easier time with that. The cell count's going to drop. You can see here that the cell count dropped by 400,000 cells. Solution time dropped significantly, more than 40 minutes. Temperatures didn't really change very much at all as a result of that. So try to keep it simple. Some simple mistakes that people make in CFD. This is general. It's not specific to CoolSim, but does happen in CoolSim. Heat loads often put at 0. Don't use 0. Put in a watt. Just 1 is fine. That'll work. Same with PDU. Aligning objects. Try to align things wherever you can. By the way, in all axes, X, Y, and Z. Look for gaps between racks. Rack sizes should be reasonable and consistent. If your rack size is varying by 2 inches from one to another, you don't need that detail. Just make them all the same size. You can let things overlap. Solid geometry can overlap one another, so that's fine. The mesher's okay with that, so let blocks overlap if you want. It's sometimes easier to do it that way to ensure that you don't have any problems with gaps in between them. And then the big thing is blocked inlets and outlets. Be careful that you don't have blocked inlets and outlets on cooling units, tiles, racks. They need a little bit of room to breathe. And I would recommend leaving at least a 3-inch gap underneath tiles so that they can breathe a little bit too. So if you're doing an underfloor cable tray underneath a floor tile, please try to keep the cable tray under the floor tile by a few inches at least. Dead zones. This is a big one. As I mentioned, doesn't seem to be as critical in CoolSim 4.5 as it used to be, but it's still there. So the user on the right has made a room for some reason with blocks. And these blocks look like columns, which means they go from slab to slab. They go from right at the bottom all the way to the top. And that isolates this volume. This volume is completely isolated from the rest of the room, and the solver will stall. It can't calculate pressure across that medium to figure out how to handle the mesh that's inside that room. So the better thing to do is block it out like this. This means there will be no mesh in there, which improves your solve time, reduces your solve time, and if you're not interested in what's in there, just block it out. If you are interested in what's in there, use baffles and let them leak just a little bit, and you'll get the same effect, but the solver will be able to solve it. Here's a model. I'm not trying to pick on anyone in particular, so if you recognize this model, please don't be offended. But this is common. I see these things. Take a look at what's going on up here. Notice the edges of these blocks aren't lined up very well. It's a little bit sloppy, and that'll cause the mesher to create a bunch of cells around there, and you don't really care about that, I don't think. I think that was just a user input, so be careful of that. Try to line them up nice and clean. We have alignment tools that allow you to do that, or you can just use the dimensions on the editor to line them up. This is also a dead zone. They used, like I mentioned before, blocks to create this section of the room, and so it's completely isolated, and that's going to make the solver stall. It may solve it, but it's going to struggle. It's going to take a long time if it's able to do it at all. They're overlapping a tile a little bit here. That's not a problem as long as it's on the edge. It looks like it is on the edge, so that's fine. So we have been able to, over time, the good news about CoolSim is that every single run goes through the same sequence, the same script, and we've been improving the script over the years so that it's more tolerant of certain situations. For example, right here I say rack overlapping tile. That's okay now. You can actually do that. You can overlap it by almost 50% and it will still run without any issue. Over here, look, we've got a situation where the rack outlet's blocked. So this rack is blowing to the wall, but it's up against the wall. So that's going to fail. There's also a gap between the rack and the cooling unit, which is probably not necessary. Another one up. This one's actually going to run okay because it's not up against the wall. It's close, but it's not sitting against the wall, so that'll run okay. I see another gap right here between the baffle and this rack. I would close up that gap. So in general, try to align things. There's another gap here. I don't know if it's important or not. I would line these fronts up because it's not important. It's not going to make a difference between whether they're offset by little or not in terms of the overall solution. And so I'd line them up. It would be easier on the mesher. So you have to think a little bit like a mesh. Think like a mesher. What's the mesh going to do? The better you understand the mesher, the better off you'll be. So it is the top of the hour. It's 10 o'clock. I would like to open it up for any questions you may have. So please use the question window to ask any questions. What we've tried to do here is give you a feel for setting up the model for solving, how to set up post, how to view your results and analyze some of the results, and how to handle failure conditions. Let me just summarize here. The level of detail in a model is going to impact the overall runtime because the number of cells will be proportionate. So you want to try to keep your models as simple as you possibly can and still make the point you're trying to make or get the information you're trying to get from it. Level of detail is always going to determine runtime, solve time, everything else. So start off with a simplified representation and then add detail after you get it to run and you get an overall feel for what's going on in the room. Coarse degree of granularity will give you a lot of feel for what's going on still. It's going to show you the flow patterns. It's going to show you where the general hotspots are. You may need to dial it in later, but at least it will give you a good overview. I always start with coarse setting of mesh. That's generally good enough. I don't use medium or fine unless there's some tricky geometry in the room or there's unusual pressure conditions in the room. So it's defaulted to coarse. That's generally good enough. And then what I always do is look at my output. First I check the summary report, the text, just to make sure the input parameters were correct, that the cracks were set up correctly, that the IT load in the racks were set up correctly. Then I look at the airflow visualization to make sure there's no issues with air not getting to where it's supposed to get. Those are the path line plots I was showing you. And it allows you to see what's going on and make sure the air is moving to where it needs to go. Now, pathline, we use an algorithm for pathline plot, and sometimes you don't see flow coming out of an outlet because the mesh isn't fine enough to show it. We do use an algorithm for how many pathlines that we need per cell, and for it's tough to come up with a common approach, a common way to have enough but not too many, because some of these output files can get very large with respect to pathlines because we're putting arrows on them. I've seen just the CVF files be as big as 18 megabytes for a single CVF file. So we try to keep the size small by reducing the path lines proportionately, and it is an algorithm. Occasionally you won't see any, but you can tell it's working because of the pressure profiles or the summary reports. So if there are no questions, and I don't see any today, I think I've covered just about everything I wanted to cover today. Let me just make sure. I'm going to back up to this slide and just my outline slide for the day and day 3 outline. Yeah, so we set up the model for run. We ran it. We looked at some of the results. Crack parameter analysis. So let me just show you what crack parameter analysis output looks like before we go. I think I have a model here I can show it to you with. So here's CPV. Now I did try to run it with the new report. This has got the old report in it, but it's okay. It just was run at 4.4 instead of 4.5. So it's got the older style report. A question here from Bill Ford. What is the general way to make a case for containment? Well, the general way is to run it without the containment and show the bypass airflow, right? Because generally without containment, you're going to show with your path lines air going right back to the cooling unit. And your return temperatures, therefore, on your crack is going to be lower than it should be. Now, I don't think I can show you that in this particular model, no. But so just in general, what you want to do with containment is show the before and the after. In the before case, without containment, the air will not necessarily all go to the rack. It will, in fact, loop back and go to the cooling unit itself. And when that happens, the return temperatures will decline. So, and I'm just going to show you here a summary report, and in the summary report under crack performance, you can see the returns. The supply is something you set. This is an input parameter. You say, I want it to, either deliver this temperature, or you set the thermostat so that the return temp, well, let's just go with supply temp. We set the supply temp. The return temp is calculated based on the CFD. So before containment, you'll see this number be generally closer to that number because the air is looping back, the cold air is looping back and cooling off the return. And after containment, this number, the return temp, will go up because you've made the air go to the device themselves, the IT units themselves. And when you do that, you get a benefit of energy. In other words, you save energy, and the ratio is about 3.5% per 2 degrees F, or some people like to use a 1-to-1, 1 degree F equals 1% of cooling savings. But you'll also generally be able to reduce this number right here as well. So let's take a look at this data center. First of all, let me tell you this is a summary report. This is what the output looks like when you run crack parameter analysis. You first get a summary page that shows you that here I've run 4 variations. I've shut crack 44 off here. I shut 45 off and run 1. I probably have some supply temp, some changing. Yeah, so you see the supply temp. So this is just a summary page. And then underneath each one of these pages is the detail. So I'm going to take a look at run 2. I've got it set at 60 degrees F. 11,000 of these cracks are running probably full tilt. So let's take a look at run 2 and let's look at some analysis. First of all, let's look at my description of data center. You see, I'm delivering a 104. Total flow through racks is 114. So I don't have enough in this particular example to satisfy the needs. So containment isn't going to help me much here, because I've got problems as it is. I don't have enough airflow to satisfy the needs of my racks. And looks like I'm dumping heat through the wall as well, overall heat transfer through the wall. So chances are when I take a look at my racks, they're going to look like that. This is a compliance plot, and you see here that they're failing. And half the racks are failing. Now, in this particular model, the air, you can sort of feel the air coming in here, and it's not making it up into here because it's going too fast. We've got a velocity problem. It's going over here, and it's cooling the bottom end of those racks, but we've got all kinds of problems in this room because of that. Containment's not going to help us much in this case because we don't have enough air to begin with. But in general, what we would see in the case of needing containment is the air would be coming from these tiles, and it would be going right back to the crack unit. Now, it's interestingly enough, there's a little of it going on right there. You see we've got bypass airflow going on right there. Air is coming out of the tiles, it's not going through the rack, and it's coming right back to the cooling unit. And we don't have enough air to begin with, so no wonder these rack inlets are hot. Part of the air is going back to the cooling unit, and you can see here that we've got too many tiles there. I mean, one of the first things I'd do is remove some tiles, but we don't have enough to begin with, and we have bypass airflow. What containment does for you is it eliminates that bypass airflow, and therefore your crack return temperatures will be higher, and if you've got more air than you need from these cooling units, you can put VFDs in them and slow them down so that you're giving the racks just exactly what they need and not more, and that will improve the efficiency because your fans are running slower, which is a cubic relationship, by the way. The power consumed by a fan is a cube of the RPM, and you will also get more efficiency out of the cooling unit itself because its efficiency is proportionate to the delta T it sees across it, and the bigger the delta T, the more efficient the unit is. So that's a quick overview of what, and again, you export this and it all comes out the same way. You'd have 4 folders and 1 master, and it would assemble completely. Another question is how is the CFM for the rack input calculated? It is calculated based on the heat transfer equation, convective heat transfer equation. So let me just open one up here and show you. So under specifications, you set the load and the temperature rise, and the flow rate is calculated because the heat transfer equation says if I have 6.8 kW of thermal load at sea level, by the way, and sea level is a parameter, or altitude is a parameter, under the room of CoolSim, so you can go to the room and edit the room parameter for altitude, and the density will change, and this relationship will change a little. But in general, it's sea level for every kilowatt of power, and let's just change this to 1 and you'll see it change. Assuming a 20-degree delta, you'll get about 154 CFM per kW. If I change this to some other number, of course, I mean, servers are getting a little more tolerant. Some of them, they claim, can go to 30 degrees. That will drop this number even lower. So it does depend on what you're using for equipment. This is an approximation, of course, because we don't know exactly what the fans are doing inside of these units. If you want to get to that level of detail, I would use Rack Builder and get into the rack and then set these up and try to mimic the behavior of the specific server you're working with if you want. That is possible. But in general, this works fairly well, and that's how you do it. All right, so I think I've answered all of the questions. I would like to thank you for attending today. I have recorded this and will put the recordings up on our website. If you have any follow-on questions, please feel free to reach out to me directly. I am paul.bemis@coolsimsoftware.com. You've probably seen that by now. Be willing to talk to any of you. If any of you are interested in CoolSim and would like a trial version of it, we do supply evaluation copies for you to experiment with to see how it behaves and how it works. And yeah, we'd love to work with you. Thanks, everyone, and have a good day.